Hi everyone, we're presenting our project on EEG classification and capture retrieval via clip alignment for Intro Deep Learning course in Fall 25. We focus on electroencephalography or EEG. While it captures electrical brain responses to visual stimuli, the data is noisy, low resolution, and highly variable across subjects and sessions. This makes it challenging to extract stable, discriminative information for high-level tasks. So, does the EEG contain enough visual and semantic signals to successfully perform image classification and capture retrieval? Previous research has shown that EEG contains stimulus related to structure usable for basic category decoding. Some work has attempted to map EEG into pre-trained and embedding spaces like clip retrieval. However, both classification and retrieval performance are limited, especially in cross-subject generalization. We aim to find out how well a unified EEG encoder can support both reliable classification and retrieval. We have two tasks. One is image category classification, in which we map the EEG signal to one of the 20 object categories. Our goal is to achieve an accuracy above the 5% chance level. Task 2 is caption retrieval. We align the EEG features with the clip text embedding space and attempt to retrieve the correct caption from a large dataset. This assesses the recovery of high-level semantic information.
We used the EEG dataset that involves 13 participants viewing 9,000 images across 20 categories. Each brain response is 122 channels by 500 time steps EEG sample. We utilize a total of 26,000 views, which are split into training, validation, and testing sets based on sessions, maintaining a strict separation to test our generalization. So this is our model architecture. The raw EEG input first goes through a CN feature extractor to capture local temporal patterns. Then the transformer backbone processes the sequence modeling complex cross-electrode dependencies. The extracted EEG representation vector are used by two heads, a single MLP classification head and a projection head for alignment with the fixed clip text encoder. For the retrieval task, we use the symmetric info NCE loss. Its objective is to push matching EEG caption pairs closer in the embedding space while simultaneously pushing away all non-matching pairs in the batch. We calculate a loss in both directions, EEG to text and text to EEG, and average them. This ensures robust and discriminative embedding alignment.
Our evaluation metrics include standard accuracy for the classification. For retrieval, we primarily use recall at K, where K is 1, 3, or 5, which measures the successful retrieval of the correct caption within the top K results. We also use MAP and clip score. First, the classification test. Through ablation, we found that a single MLP classification head significantly outperformed subject-specific heads, which suffered from severe outfitting. Our final model achieved 11.38% of test accuracy, which is a is a result that is outperforming the 5% chance level and exceeding the CNN baseline's 9.92%. This confirms that the brain signal does retain discernible coarse visual information per subject accuracy. So as you can see right here, the chart on the left demonstrates the low variability between the subjects. All participants' accuracy scores exceeded 5% chance level, and most perform near 10%. And on the right side, the confusion matrix reveals the semantic confusion among certain categories. For example, the person category exhibits a very high correct prediction rate, suggesting new response to human figures is highly distinctive and easy for the models to classify correctly. On the other hand, the model frequently confuses train with boat and dog with cat, showing that the challenge of distinguishing semantically similar items using only EEG signals. In contrast, the caption retrieval results were extremely challenging. All clip fine-tuning strategies, including frozen clip and LoRa, yielded near zero instance recall at 1 and very low recall at 5. This critical finding suggests that the retrieval performance is bottlenecked by the inherent noise and instability of the EEG signal and the limited data volume, rather than the capability of the clip model itself. The highest, although tiny, gain was achieved by fine-tuning only the last layer of the clip text encoder. In summary, we confirm that EEG data contains both visual and semantic signals, which we successfully extracted for classification. However, we find that the EEG data is noisy and unstable, leading to poor generalization across sessions. We believe that EEG still holds great potential for real-world tasks with more data and sophisticated modeling. Our future work will focus on more advanced data processing techniques and further optimizing the alignment between the EEG encoder and the clip embedding space. Thank you all for watching our presentation, and here are our references.